In this coming set of lectures, we're going to study the deformation and strain of objects. In particular, we're going to use the elements of linear algebra to try and understand or describe two things. The first thing is the description, or the mathematical description of objects in space. And the second thing is the mathematical description of deformation of objects and, to be specific, continuum objects in space. And so to do this, we're just going to introduce just a few small concepts before we start the section on the description of motion. So the first thing you need to know is, how can I describe an object in space? So an object in space is made in general out of material points. Physically, there are material points that constitute the object. In order to describe this object mathematically, we say that we embed this object in a three-dimensional Euclidean vector space, where this is E1, this is E2, and this is E3. And then we say every point on this object is represented in this Euclidean vector space by a vector capital X, where this vector capital X has a component in the first direction plus a component in the second direction plus a component in the third unit direction. And the set of vectors that describe the object or that represent the object is denoted by omega naught. So omega naught is the set of vectors that represent the embedding of the vector, so of the object. So all the vectors that represent the material points of that object, I put them in one set, and I call the set in general omega naught. And to give you an example, I would like to represent an object, for example, a wire object. A wire object is made out of a set of vectors. That give me this wire, and this set of object, or this set of vectors, can be written as X, capital X, with 3 components, and each component is a function of one parameter, which could be any generic parameter, which, for example, the length of this wire. So if this is the starting point and this is the end point, at xc. So xc is a variable that runs along the wire. So the first vector representing the start point of that wire is a function of xc equals 0. So this point, the vector xc is equal to x1 of 0, x2 of 0, x3 of 0. The middle one, for example, will be a function of, or let's start the end point. The end point will be a function of x1 of xc equal L, x2 of xc equal L, x3 of xc equal L, and so on. The middle point will be a function, for example, of xc equal to L over 2. Another example. Also another wire object, but with a curve, a known curve. For example, this curve from 0, 0 to 1, 1, where y is equal to x squared. The set of vectors representing this line can be represented by xc, where xc is the vector x1 of t, x2 of t, where x1 of t is equal to t, and x2 of t is equal to t squared, where t is between 0 and 1. And you can describe, in this case, omega naught as all the vectors x such that x is equal to t squared, and t is between 1 and 0. So if you try to look at examples of vectors in omega naught, put t equals 0, x is equal to 0, 0, is an element of omega naught, is an element of this object. Put t equal 0.5, x is equal to 0.5 and 0.5 squared, is an element of omega naught, and so on. And so any element in space can be described as a set of vectors. These set of vectors represent the different points within that object. So if omega naught describes the set of vectors representing the object before deformation, if we imagine that this object moves and deforms in space such that its material points move relative to each other and occupy new positions in space, we can call the new set that describes the position vectors of the new object, or the object in its new position, we can describe it with the set omega. And in general, what we're looking for is a function that describes this movement. And we call the set of vectors that describe the object before motion, we call it the reference configuration of the object. And after deformation, we call it the deformed configuration. And in general, what I'm looking for is a function, a mapping that tells me if this is the point before deformation described by the vector capital X. X is equal to capital X1 E1 plus X2 E2 plus X3 E3, and it's the point after deformation is described by a new vector called small x, which is equal to X1 E1 plus X2 E2 plus X3 E3. I'm looking for the function X as a function of capital X. This function is what describes the deformation. So usually I'm looking for f that takes x in the reference configuration and gives me a small x in the deformed configuration such that x is equal to f of x. Now, of course, the displacement vector is equal to the difference between the new position and the old position, which is f of x minus x. Now, in general, an object can have all sorts of it's possible to find any kind of function that describes this deformation. But for continuum objects, if my object is continuum, or if the function f describes a continuum object, then we put some restrictions on this f. Not only a continuum object that does not develop cracks or holes, as it deforms, then we restrict f, the function, to be bijective and smooth. So let's understand what bijectivity and smoothness means. Bijectivity means for every point in the reference configuration, there has to be a unique point in the deformed configuration. For every point in the reference configuration, there has to be a unique corresponding point in the deformed configuration, and of course for every point in the deformed configuration there has to be a corresponding point in the reference configuration. That is what bijectivity is. And I'll give you an example of an object that once it deforms, it does not maintain this bijectivity. If you have a piece of metal, a box or a block of metal that you deform into a sheet, this f is not bijective because this whole line is deformed into one point. So this one point, I cannot find a corresponding one point in the reference configuration. So most of the elements, the elements that we're going to study in this course are not applicable to such a deformation. F also has to be smooth. In fact, it has to be continuous and smooth. So, for example, the elements of the continuum mechanics that I will study in this course will not be cannot be used, for example, to describe the deformation of a box of smaller objects, such that the smaller objects change their neighbors. As the objects change their neighbors, the continuity of f is lost, because in the reference configuration this point is close to this point. In the deformed configuration this point is far from this point. They are not neighbors anymore. So once elements lose their neighborhood, then it's no longer continuous, and I can't use the elements of continuum mechanics without modification to describe this motion. I can, however, if I have two objects that are connected to each other, I can find two different functions that are continuous and smooth, bijective, continuous and smooth, for each of the objects, and to maintain some compatibility, while maintaining some compatibility on the boundaries between those two objects. So in general, the elements of continuum mechanics that I will study here are not applicable of course without modifications. I have to modify them to make them applicable to objects like this where that have crack extensions, for example. Because once the crack extends, I'm losing the bijectivity or the continuity of the deformation function, or crack extensions, or in general appearance of holes within object. So all our continuum mechanics work that we're going to study in this course, it's basically solid mechanics, where we're going to assume that my object keeps its neighbors, the points on this object keeps its neighbors and does not form any holes or cracks as the object deforms. So we're going to study a few simple description of motion. Simple functions that describe we're going to study some functions that describe simple deformations. The first kind of deformation or displacement is what I call rigid body displacement. If I have an object in space embedded or described by omega naught, all the vectors on this object is described in the set. I put them all in the set omega naught, and I embed omega naught, where omega naught is a set of vectors in R3. Okay, of course, this is a set that is a subset of R3. And if this object this is X, now if this is the original object, and if this object moves or translates by one vector C, all the points on this object is moved by one vector C, such that the new X is equal to capital X plus C, then in this particular case X is equal to capital X plus C, or in other words x1, the new position vector that's made out of 3 components, is equal to the old position vector made out of 3 components plus 3 constants. And the displacement vector, which is equal to the new position minus the old position, is equal to C. So this displacement vector, this constant vector C, gives me the displacement of each point in my object. So this is what constitutes rigid body displacement. A rigid body rotation is described by the following. If I have an object in space, E1 and E2, and this object, each point in this object is described by vector x, and I take all those vector x's and I put them in one set, I call it omega naught, which is a subset of R3 and gives me all the vectors that correspond to the physical points of the object. If after deformation all what happened to the object is that it rotated, so if this is x and this is the object before rotation, so this rotation is described by saying that the new vector x, or the new position vector x, is equal to a rotation matrix multiplied by the old vector x. This is the reference configuration. This is the deformed configuration. And Q is a rotation matrix. So in general, x1, x2, x3 is equal to q11, q12, q13, and so on, multiplied by the original position. And the new the displacement vector, which is equal to the old position minus the new position. The new vector x is equal to q multiplied by the old vector x. The old vector x is equal to a matrix I multiplied by itself, which means I can take q minus I vector multiplied by the original vector x, which gives me the position vector x. The new position vector, the q minus I multiplied by x gives me the displacement vector u. The next type of this displacement is the rigid body motion. And the rigid body motion is described by the combination of both rigid body displacement and rigid body rotation. So this is rigid body displacement plus rigid body rotation, which means I have an object here that did both translate and then rotate, and so this is C and this is rotation. So the new position vector x will be equal to a rotation multiplied by the old vector x plus a constant, and u is equal to the new position minus the old position. The new position is equal to qx plus c minus x, and so the displacement vector is equal to q minus I multiplied by x plus c. Where, of course, q is a rotation matrix, q is a 3 by 3 matrix, and c is a constant displacement vector. So far, all the deformations that we described are not accompanied by any strain, because the neighboring points do not actually move relative to each other. Each 2 points keep the same distances between each other. The next type of deformation, which, as we will study later, does have associated strain, is a uniform extension or contraction. If I have an object that's sitting in E1 and E2 and in E3, but I'm only going to just view it in R2, Euclidean vector space, and let's say every point or let's say this length extends, so this is the object before deformation, and after deformation the length in this direction is extended and the length in the opposite direction is contracted, so this is the new object. Such that the new position x1 is equal to a multiplier by x1. The new position x2 is equal to a multiplier by x2. The new position x3 is equal to a multiplier by x3. In this case, the new position vector x, so this is omega naught, this is omega, k1, k2, and k3 are real numbers. The position vector x, which is made out of x1, x2, x3, is equal to a matrix multiplied by the old position vector, where this is k1, 0, 0, k3. So if this motion, or if this function, or let's say when no motion happens, then k1 is equal to k2 is equal to k3 is equal to 1. So when the new position is equal to the old position, that means k1, there no motion happens, and that means k1, k2, k3 are all equal to 1. If one of the directions extended, for extension, ki is greater than 1. For an object to extend, that means this multiplier is greater than 1. x1 is, for example, equal to 1.1, capital x1 1.2, so there's an increase of 10% or 20%. For contraction, ki is less than 1, but of course it can't be reach 0, because if we use 0, that means that all the material is squished from one direction. It's squished to 0, which is not allowed using the elements of continuum mechanics that I'm studying here. The last type of simple deformation that I would like to study is called uniform shear. Uniform shear is described using, so visually, if I have an object represented by a set of vectors embedded in R3, or the object is embedded in R3. The object is embedded in R3 and has omega naught to describe its position vector before in the reference configuration. In the deformed configuration, uniform shear is described by the movement of all the points perpendicular to a certain direction. So all the vectors that are perpendicular to a certain direction move along another direction. So all these vectors move in this direction. Such that the new, so this is E1, this is E2, such that the new x1, let's see, this is capital X1, this is the position of the vector before, sorry, x2, this is the position of the vector before deformation. After deformation, this is the position. This is theta. This distance is equal to x2 tan theta. And so the new position x1 is equal to the old position x1. So for example, this point, this is capital X1, this is capital X1 plus a little bit more, and this little bit more is equal to x2 tan theta. x2 tan theta. x2, the position vector or the position distance x2 stays the same. So the new position is equal to the old position. x3 is equal to the old x3, which can be described as, or can be written in matrix 4 this way: x1, x2, x3. The new position vector is equal to 1 tan theta, 0, 0, 1, 0, 0, 0, 1 multiplied by capital X1, capital X2, capital X3. I'm going to call this matrix M. Therefore x is equal to mx, and the new position vector is equal, the displacement vector is equal to the new position vector minus the old position vector, which is equal to mx minus x, which is equal to m minus I multiplied by x. So these are some simple deformations that we studied. In the next sections, we're going to extend what we studied to try and understand what constitutes strain, when does a material exhibit strain, and when does the material just exhibit rigid body displacements.